Assalamualaikum warahmatullahi wabarakatuh and a good day to all of you. So today we will continue our lesson with subtopic 3.2, which is a partial derivative. At the end of this subtopic, I am expected you to know how to find the partial derivative and also how to find the higher order partial derivative of the function f. Before we continue with this subtopic, let's do some revision about the first derivative of a function with one variable fx. Okay, so let's have an equation y which represent a function of f with one variable x. Okay, so let's consider a curve that represent this function fx. So we have a curve with x and y axis here. Let's this curve represent a function fx. The line that touch a point on a curve, we call it as a tangent line. Okay, this one is a tangent line to the curve fx. Okay, and the gradient of a tangent line is actually a first derivative of a function f with respect to x by using a first principle of derivative. Okay, this principle come from the formula of gradient to find a gradient of a line. Okay, we have a formula to find a gradient of the line m equal to y2 minus y1 over x2 minus x1. So we will use this formula to find a gradient of this tangent line. So let's say we take 2 points on a tangent line here and here. Okay, where the first point is x and fx, and the second point is x plus delta x and fx plus delta x. So to find a gradient of this tangent line, we need to use this formula. So we will have fx plus delta x minus fx divided by x plus delta x minus x. Okay, so we will have fx plus delta x minus fx over delta x when we consider a limit of delta x approaching 0 exists. This is the gradient of the tangent line, or the first principle of the derivative of function f with variable x. Okay, so we will use the same principle to find a first derivative of a function f with two variable later. Okay, just a quick review. Let's say we have a function fx equal to 4x squared plus 2. Okay, so by using a formula of differentiation, we will simply get the differentiation of f, which is f prime x, equal to 8x, but it's actually come from a first principle of the first derivative. Okay, let me show you how to use the first principle of the derivative for function f with variable x. So let's say we now have fx equal to 4x squared plus 2. In the first principle of the derivative, we need to find what is fx plus delta x. So we will have fx plus delta x equal to 4 times x plus delta x squared plus 2. So we expand this equation, we will have 4x squared plus 2x times delta x plus delta x square plus 2. Therefore, we will have 4x square plus 8x delta x plus 4 delta x power of 2 plus 2. So this one is our fx plus delta x. So now, let's substitute this inside the formula of first principle. So we will have limit delta x approaching 0. So fx plus delta x is 4 x squared plus 8x delta x plus 4 times delta x squared plus 2 minus with fx, so our fx is 4x squared plus 2 divided by delta x. So we open the bracket, we will have limit delta x approaching 0, 4x squared plus 8x delta x plus 4 times delta x power of 2 plus 2 minus 4x squared minus 2 divided by delta x. Okay, now 4x squared minus 4x squared 0, 2 minus 2 is also 0. So we only left with limit delta x approaching 0, 8x delta x plus 4 times delta x squared over delta x. Okay, now we factorize delta x, so we will have limit delta x minus approaching 0 delta x, so we only left with 8x plus 4 delta x over delta x, so this one can be cancelled out, so we only left with limit delta x approaching 0, 8x plus 4 delta x. So when delta x approaching 0 exists, so we will have 8x plus 4 times 0 equal to 8x. So this is the first derivative of a function f with one variable x. Therefore, actually, the first derivative of a function f with one variable represent the gradient of a tangent line. Okay, so we will continue with the first derivative of a function with two variables in the next subtopic. Okay guys, we just learned about the first derivative of a function with one variable. So now we want to continue with a first derivative of a function with two variables. Okay, for the first derivative, we know that the first derivative actually represent the slope or a gradient of a tangent line. Okay, so let's say we have a function of two variables, which is we are dealing with a surface z, where surface z represented by a function of two variables x and y. So we can find the derivative of a function f either with respect to x or with respect to y at one time. So we are called this first derivative as a partial derivative. So when we are differentiating our function f with respect to x, we will have a partial derivative with respect to x for a function with variable x and y, where we consider y as a constant. And when we differentiate f with respect to y, we will have a partial derivative of a function f with respect to y with point or with variable xy, and we are considered x as a constant. Okay, so by using the same principle as the first derivative for a function with one variable before, the formula for partial derivative of f with respect to x with two variable xy is equal to limit delta x approaching 0 f x plus delta x y minus f xy divided by delta x. And for the partial derivative of a function y with respect to y, we will have limit delta y approaching 0 fx y plus delta y minus fxy divided by delta y. Okay, so this only a principle or the theoretical formulation for the first derivative of a function f with two variables. Okay, we will use the same method to differentiate this function. Only you need to remember, every time we are differentiating our function with respect to x, we will consider y as a constant, and every time we differentiating our function with respect to y, we will consider y as a constant. Okay, so the first derivative actually represented a slope of a tangent line. So for the partial derivative of f with respect to x, is actually represent a slope of a tangent line at a given point, either in x direction or in y direction. It also measure the rate of change of z, either with respect to x and also with respect to y. Okay, let's move to an example to find a partial derivative of f with respect to x and with respect to y. Let's say we discuss an example 3.2.1, where we have a function fxy equal to 2x cubed minus 5x squared y squared plus 2x minus 4y. So we have been asked to find a partial derivative of f with respect to x and also with respect to y at point 1, 2. Okay, so now the first thing is you need to find the partial derivative of f with respect to x. So we will differentiate this function with respect to x and consider y as a constant. So we will have 6x squared minus 10x y squared plus 2, and negative 4y will be equal to 0 because negative 4y is a constant. Differentiate a constant is equal to 0. Okay, then we differentiate the function f with respect to y. So we will have a partial derivative of y with respect to y equal to negative 10x squared y minus 4. Okay, so now we have been asked to find the value of partial derivative at point 1, 2. So what you need to do is just substitute the value of x equal to 1 and the value of y equal to 2 into the both partial derivative function here. So for partial derivative with respect to x at point 1, 2, we will have 6 times 1 power of 2 minus 10 times 1 times 2 power of 2 plus 2. So we will have 6 minus 10 times 4 plus 2 equal to negative 32. Same goes for the partial derivative of f with respect to y at point 1, 2. We will have negative 10, 1 power of 2 times 2 minus 4. So we will have negative 24. So this is how to find a partial derivative with respect to x and with respect to y at some given point. Okay, so let's move to another example here. So we have example 3.2.2, where we have a function fxy equal to y power of 5 ln x, and we have been asked to find a partial derivative of a function f with respect to x and y at point 2, 2. So the first thing is to find what is the partial derivative of f with respect to x. Okay, always remember whenever we differentiating our function with respect to x, our y will always be a constant. So here we will have y power of 5 ln x, differentiate, we'll have 1 over x. So we left with y power of 5 over x. Okay, next we move to find a partial derivative with respect to y with variable xy. So we will consider x as a constant. So differentiate y power of 5, we will have 5 y power of 4 ln x. Okay, now we have been asked to find a partial derivative with respect to x and y at given point 2, 2. So just substitute a value of x equal to 2 and a value of y equal to 2 for the partial derivative of f with respect to x. So we will have 2 power of 5 divided by 2 equal to 2 power of 4 equal to 16. Okay, same goes to the partial derivative with respect to y at point 2, 2. We just need to substitute the value of y equal to 2 here and also x equal to 2. So we will have equal to 55.54518. So this is how to find a partial derivative with respect to x and with respect to y at some given point. Let's continue with a subtopic 3.2.1 where partial derivative as a slope. Okay, so we know that when we have a surface Z represent the function with two variables x and y, we can find the partial derivative of f with respect to x or with respect to y. So let's say we find a partial derivative of f with respect to x at some point x0, y0. So we will have fx at point x0, y0, and this partial derivative with respect to x actually represent a slope of a function fxy for the plane y equal to y0 at point x0, y0. Okay, and if we find a partial derivative of f with respect to y, we will have fy at point x0, y0, and this partial derivative with respect to y actually represent a slope for the plane x equal to x0 at point x0, y0. Okay, because we always consider y as a constant every time we are differentiate our function f with respect to x. So this one we will always let y equal to y0, and every time we differentiate our function with respect to y, we will always consider x as a constant. So this is for the plane x equal to x0. Okay, the partial derivative with respect to x and with respect to y also always represent the slope for the tangent to the surface z, where the line is parallel to xz plane if it is a partial derivative with respect to x, and the tangent line that parallel to yz plane if we are find a partial derivative with respect to y. Okay, so let's see an example 3.2.1. Let's see the example 3.2.1 when we have to check either the function fx is increasing or decreasing at point 2, 3. Okay, so let's say we have a function fxy equal to y squared over x power of 3. So we want to check either this function is increasing or decreasing at point 2, 3. So what we need to do is to find the gradient of this function. Okay, the gradient of the tangent line for this function. Okay, whenever the gradient of the tangent line for this function is negative, means that our function is decreasing, while when we have a gradient of the tangent line for this function is positive, means that our function is increasing. Okay, so for the question A, we have been asked to check either the function is increasing or decreasing. If we allow x to vary and hold y fixed, means that we need to find a partial derivative of f with respect to x and consider y as a constant. So what we need to find here is a partial derivative of f with respect to x. So this function can be also written as y squared dot x negative 3. So when we differentiate with respect to x, we consider y as a constant. So we will have negative 3 y power of 2 x power of negative 4. So we will have negative 3 y squared over x power of 4. Okay, so we now want to check either this function is increasing or decreasing at point 2, 3. So we need to substitute the value of x equal to 2 and value of y equal to 3. So we will have negative 3 times 3 power of 2 divided by 2 power of 4. So you will have negative 27 over 16. Okay, so because of the gradient of the tangent line is negative, means is less than 0, it means that our function f xy is decreasing at point 2, 3. Okay, So for the question B, we need to check either this function is increasing or decreasing at point 23. If we allow y to vary and hold x fixed, means that we need to find the partial derivative of f with respect to y and consider x as a constant. So now we have fxy equal to y squared times x negative 3. Okay, so we want to find the partial derivative of f with respect to y. We will consider x as a constant, so we will have 2y dot x negative 3 equal to 2y over x power of 3. Okay, and at point 23, our partial derivative with respect to y will become 2 times 3 divided by 2 power of 3 equal to 6 over 8. Okay, so 6 over 8 is greater than 0, means that our function f xy is increasing at point 2, 3. Okay, because the first derivative is always represent the slope or the gradient of the tangent line. So if the gradient of the tangent line positive, means that our function is increasing, while if the gradient of the tangent line is negative, means that our function is decreasing. Okay, so let's move to another example. Let's say we do example 3.2.1.2. So we need to find a slope of the traces to z equal to 12 minus 3y squared minus x squared in the x direction and in the y direction at point 1, 2. Okay, so let's say we have a function fxy equal to 12 minus 3y squared minus x squared. So now we have been asked to find a slope, where a slope is a gradient of the function in the x direction at point 1, 2, means that we need to find a partial derivative of f with respect to x. So we will consider y as a constant, so we will have here negative 2x. Okay, so at point 1, 2, our partial derivative with respect to x will become negative 2 times 1 equal to negative 2. So this is the slope of the z in the x direction at point 1, 2. Next, we will find the slope of a function f in a y direction. So the first thing we need to find is a partial derivative of f with respect to y, where we will consider x as a constant, so we will have negative 6y. And at point 1, 2, we have a partial derivative with respect to y equal to negative 6 times 2, which is equal to negative 12. So this is the slope for the function fx equal to 12 minus 3y squared minus x squared at point 1, 2. Okay, we have learned before a derivative of a function f with one variable f prime x or del f del x represent a gradient of a tangent line as well as a rate of change of f with respect to x. Same goes to a partial derivative for a function f with two variables x and y. If we find the first derivative of f with respect to x, we will have fx for x and y, or del f del x, where this one represents the rate of change of f with respect to x. Also, if we differentiate our function f with respect to y, we will have a partial derivative with respect to y for variable xy, or we have del f del y, which represent a rate of change of f with respect to y. Let's see an example 3.2.2.1, where we are given the volume of V of a certain gas is related to its temperature and its pressure P by the gas law PV equal to 10 T. Okay, now we need to find what is the rate of change of pressure with respect to temperature. We need to find what is the rate of change of P with respect to V, which is we need to find what is del P with del T. Okay, we need to find what is del P del T, or the differentiation of P with respect to T. So the first thing we need to do is to find the formulation of P, where from the formula given we have P equal to 10 T over V. Okay, now we want to find what is del P del T, or the differentiation of P with respect to T. So we will consider V as a constant. So what we will get is 10 over V. Now we want to find what is the rate of change of pressure with respect to temperature when T equal to 300 at V equal to 20. So we just need to substitute the value of V equal to 20. So we will get the rate of change of pressure with respect to temperature equal to 10 over 20, or equal to 1 over 2. Okay, so we can simply find the rate of change by using a partial derivative of a function with two variables. Okay, let's see another example in exercise 3.2 number 7. Okay, let's do this exercise together. The volume V of right circular cylinder is given by the formula V equal to pi r square h, where r is the radius and h is the height. So the question A asks us to find a formula for the instantaneous rate of change V with respect to r, if r changes and h remain constant. So now the question asks us to find a rate of change of V with respect to r. So what you need to find is what is the change, or what is the rate of change of V with respect to r. Okay, so now we already have a formula of V equal to pi r square h. When we want to find the rate of change of V with respect to r, we will let h as a constant. So we differentiate V with respect to r, we will get 2 pi r h. So this is the rate of change of V with respect to r. And equation B asks us to find a formula for the instantaneous rate of change V with respect to h, if h changes and r remain constant. So just now we already find a rate of change of V with respect to r. Now the question asks us to find the rate of change of V with respect to h. So when we want to find what is the rate of change of V with respect to h, we will consider r as a constant. So now we have V equal to pi r square h. So to find what is the rate of change of V with respect to h, we will have pi r squared. Okay, so this is the rate of change. Let's continue with the last subtopic in 3.2, which is 3.2.4, the geometric interpretation of second order partial derivative. For second order partial derivative, we will have fxx, which is the partial derivative with respect to x 2 times. We will have fyy, which is differentiation of y, the differentiation of f with respect to y 2 times. We also will have fxy, where we have differentiate f with respect to x, then we differentiate it again with respect to y. And we also have fyx, which is the differentiation of f with respect to y, then we differentiate it again with respect to x. Okay, so if we have a partial derivative fxx, it means that this is the rate of change of f in x direction, while for fyy, this means the rate of change of f in y direction, while for fxy, this means the rate of change of f in x direction as it moves in y direction. And also if we have fyx, this means that this is the rate of change of f in y direction as the function move in x direction. Okay, let's move to example 3.2.1. Point 4.1. Okay, so we have a function fxy equal to 6x squared minus 3xy plus 4y cubed. Okay, for question A, we have been asked to find what is the value of del square z or del square f del x del y. Means that we need to differentiate the function with respect to y first, then we will differentiate it again with respect to x. Okay, so the first thing we need to find is what is the differentiation of f with respect to y. So we have del f del y equal to negative 3x plus 12y squared. Okay, every time we differentiate f with respect to y, we will consider x as a constant. Next, we need to find what is the differentiation of this function with respect to x. So, differentiate with respect to x the partial derivative of f with respect to y, we will have negative 3. Okay, so for question B, we have been asked to find what is the value of differentiation of f with respect to y, then with respect to x. Means that we need to find what is the differentiation of x, then we differentiate it again with respect to y. Okay, so we need to find what is the differentiation of f with respect to x first. So we will let y as a constant. What we will have is 12x minus 3y. Okay, then this function will be differentiated with respect to y. So x will be a constant, so we will get negative 3. Okay, so if you see from this example, del square f, when we differentiate x, then we differentiate y, is equal to del square f dx dy. This equality only hold if fxy and fyx are continuous. Okay, let's see question C. Question C asks us to find what is the partial derivative of f with respect to y. Means that we need to differentiate f with respect to y 2 times. Okay, so we need to differentiate first f with respect to y, then we differentiate it again with respect to y. So first we find what is del f del y. So what you will get is negative 3x plus 12y squared. Then we differentiate it again with respect to y. So you will get 24y. Okay, for question D, we have been asked to find what is fyx at point 32. What means by fyx? This means that we need to find what is the differentiation of f with respect to y first, then we differentiate again this partial derivative with respect to x. Okay, so what is our del f del y? Our del f del y is equal to negative 3x plus 12y squared. Now we need to differentiate this function with respect to x. So differentiate this partial derivative with respect to y. To x, we will get negative 3. Okay, so there is no variables, unknown variables here, means that at point 32, your fyx is equal to negative 3. Okay, let's discuss one question in exercise 3.2 for higher order partial derivative. Let's see question number 4. Okay, we have fxy equal to 4xy squared plus 3y minus 2x squared. We have been asked to find what is fxx and also what is fxy. Okay, fxx means the differentiation of f with respect to x 2 times. Okay, so we need to find what is the differentiation of x with respect to x. Then we will differentiate it again with respect to x. So now we have f equal to 4xy squared plus 3y minus 2x squared. We need to find what is our del f del x. So we differentiate with respect to x, y will be a constant. So we have del f del x equal to 4y squared minus 4x. Then we need to differentiate this function again with respect to x. Okay, so this will become negative 4 because y is always a constant and differentiate constant is equal to 0. So this is your fxx. Now we want to find what is our fxy. Okay, this means that we need to differentiate our f with respect to x first. Then we will differentiate again this function with respect to y. Okay, so now we already have our del f del x equal to 4y squared minus 4x. So differentiate this function with respect to y. We will get 8y. This one is our fxy. So this is how you find higher order partial derivative of your function with two variables.